Hello everybody and welcome to this talk on the added distance to k-Subsequence Universality. My name is Stefan Siemer and this is joint work with Joel Day from Loughborough University, Pamela Fleischmann from Kiel University, and Maria Kosche, Dorokos and Florin Manea from Göttingen University. So let us dive right into some notions and definitions such that we can define the problem. So first of all we need the definition of a subsequence. So a subsequence is a word, and we can find that word in another word by allowing for some gaps. Yeah? So, for example, we have a gap in the beginning, then we find the first part of our subsequence, then we can jump over some other letters and have another gap, then find the second part, and so on, until we find the whole word V in our word W. And if so, then we call it a subsequence, and we denote the set of all subsequences of a word by this notion subseq of W. Further, if we want to if we are only interested in the k-length subsequences, then we make this small subscript k, and by that extend this notion. So let us have a look at a small example. So the subsequences of length 2 of the word abaca you can see here on the right hand side, and for example this AA we get by simply jumping over this B to the other A, so this A, jump over B to the other A and then jump to the end. Or for example this AC, we find this A, then jump over BA to the C and then to the end. Okay, so what can we do with these subsequences? We can define a relation called Simon's congruence. So we call two words W and W prime equivalent under Simon's congruence with respect to some subscript k if their subsequences of length k are equal. And this is relation defined by Imre Simon, and it's quite common in some areas. So let us also have a look at an example here. So we have these words W and W prime, and we can simply calculate all the subsequences of length k of W and of W prime, and as you can see these subsequences are exactly the same set. So we can say that these are two Simon congruent. Further we can say that these are not three Simon congruent, because as we can see in W prime we have the subsequence BBB, and we don't have that in W, so there is at least one subsequence distinguishing these two words. Speaking of Simon's congruence, I can make some shameless advertisement for another paper that we submitted here to STACS. It's efficiently testing Simon's congruence, and there we have a linear algorithm for finding the largest k for which two words are Simon's congruent. Okay, so let us go on and have a look at some modification. So we have this W and W prime, and we know that these are two Simon congruent. So what happens now if we modify the right hand word a little bit and append a C, for example? Then we can see that these two words are no longer two Simon congruent, because this CC subsequence distinguishes both words. So a natural question to arise is how many added operations do I need in order to make two words Simon congruent again, or two Simon congruent again in this case? And yes, as normal added operations, insertions, substitutions and deletions, we can see that, for example, we can insert for the left-hand word a C at the end. Then we can see that the sets of subsequences are the same again. Or we could just delete this C on the right-hand side that we just appended in the previous step. Okay, so more formally, we want word-word distance such that the two words are k-Simon congruent after the added operations. And from this word-word distance under Simon congruence, we can define a word-language distance, because basically we only need to modify our W such that it's equal to any word that is k-Simon congruent to our word u. So we can define that as a language. Yeah, so the language of all k-Simon congruent words to u is denoted by this LUK, and we simply want to find the minimum distance of our w to any word from that language. Okay, so why is that interesting? First of all, it's almost always interesting to throw some added distance metric on string relations and see what happens. And yeah, so that's always a natural step to consider. And secondly, these languages LUK are so-called k-piecewise testable languages, and they are a quite important subclass of regular languages. So these k-piecewise testable languages can therefore be represented as an automaton, and we can solve the distance, the word language distance, between this word w and the automaton by algorithm that runs in size of the word times the states of the automaton squared. Yeah, but there's one problem. This number of states q might be exponential in alphabet size, and therefore we are interested in maybe there's something better where we don't use an automaton, but we simply plug in our w, u, and k into some algorithm and see what happens. And so far it's unclear what is the runtime for that, but we can clearly see that it must be in NP, because we could in the worst case we just delete the word w and insert the word u. So the most amount of added operations we need is the length of w plus the length of u. Okay, so since this is not a quite hard problem and it's unclear, we chose a relevant non-trivial subclass of these piecewise testable languages, and this subclass is the language of k-Subsequence universal words. And what that is, I will explain in a moment. But for now, it's important that this class is still non-trivial, because it might have some exponential representation size, and it's prominent and therefore interesting enough in language theory and piecewise testability. Okay, so what is k-Subsequence universal word? So we can call a word k-Subsequence universal if the set of k-length subsequences in a word is exactly the set of k-length words that we could construct with the same alphabet. Yeah, so simply all possible substrings of length k that we can build with this alphabet, they occur somehow in our word. Okay, let us have a small example here. So we have this word abacup, and we can see that it's clearly one universal because we can find every letter in it at least once. But it's not two universal, since, for example, the subsequence cc is not in it, and therefore we don't have all two-length subsequences over that alphabet. On the other hand, if we append a c, then we can see that this word is two universal, but it's not three universal, since, for example, BBB, CCC, and so on, they are not in the set of subsequences of three subsequences, and therefore this word would be two universal, but not three universal. So then these k-universal words have some nice structure, as we can see by a Theorem by Hebra from 1991. And this states that a k-universal word is always has always the form of k one-universal words concatenated one after another. And we will use this property also later for some results. Also, this theorem gives us a greedy strategy for partitioning a word into these arches, so-called arches. Sorry. And for that, we simply go through our word from left to right, and always, if we found the whole alphabet, we can make a cut. Yeah, so for example, in this case, the alphabet is ABC again, and we go from left to right. We see ABC, we make a cut. Then we see AC, and so on until we find a B, we make a cut, and so on. And then we have 3 arches and a little bit of rest. And this current universality index of a word W, we denote it by this iota of W. Okay, so now that we know the universality index of our word W, we are interested in how to decrease or increase that universality such that we reach our desired k-universality. And the first observations are that in order to increase the universality of our word, it's only required to use insertions operations. These insertions operations will always just enrich the set of subsequences. And if we want to decrease the universality, then it's enough to consider deletions. And in the case of substitutions, we can both increase and decrease the universality of our word. And this is interesting to consider because it yields the word language Hamming distance. Okay, so in the rest of this talk, I will mainly focus on insertions and then mention some ideas on deletions and substitutions. So let us start with a main theorem for insertions. So basically, if we want to increase the universality of our word, then we would like to compute the minimal number of insertions needed in order to obtain a k-universal word. And we can do that in O of n times k. If the k is smaller than n and if the k is larger than n, then we can simply state that each letter of our original word belongs to, let's say, one arc, and we simply have to insert always the remaining alphabet in that arc that is not there yet, and in the end concatenate the whole alphabet over and over again until we reach k-universality. And for that we only need to calculate this k times alphabet size minus the original word size. Okay, so then let's have a look at some initial thoughts. First of all, we see that the one universality is, so the distance to reaching one universality is simply the number of missing letters in that word. And we will use in the following these notions of the amount of distinct letters between the positions I and j in our word by this delta ij, and therefore the amount of missing letters is simply the alphabet minus this delta ij. Okay, so the basic idea is that we would like to create a dynamic programming where we search for some k-1 universal prefix, and we use the tail to create another one universal word. So let's see why that would work. So first of all, the k-universal word that we will obtain in the end, we will denote it by w prime, and we will get this k-universal word from our original word w. And we can see that we have some prefix in w prime from 1 to m prime that is k-universal, but if we remove the last letter, then it's no longer k-universal. And this prefix in w prime corresponds to some prefix from our original word w, in the sense that we created that prefix from our original prefix. And what we can see is that all the tails after these prefixes, we don't need to touch them with any operations. We don't need to touch them at all. So therefore, we can see that that this w prime I to m prime must have a k-1 universal prefix followed by a one universal rest. Yeah, this is exactly what the arc factorization is giving us, and therefore we can use this dynamic programming approach. So maybe that is not that clear by words, so let's have a small sketch. So we see our first base case, the first row in our matrix. We can simply say that for each prefix we see how many letters are missing here, and that is the amount of insertions that we need to do. And then we have this recurrence step, where this is illustrated down here. So basically we have some t-1 universal prefix, and we want to have a one universal tail, such that we get t universal word overall up to position L. Yeah, so we have this, we will calculate for this prefix 1 to L. What is the optimal prefix of that prefix up to L prime, such that we have up to L prime a t-1 universal word, and from that onward a one universal word. Okay, so having this at hand, we can simply state a direct implementation of this table, or direct computation of that table, and this would require O of n squared times k runtime. And now the question, can we do better? And the answer is yes. For example, the first approach is that we could construct direct acyclic graph with weighted edges. So the edges of ij simply get the weight assigned that the amount of missing letters between I plus 1 and j. Yeah, so we can construct this DAG, and then in this DAG we can search for the minimum weight k-link path, and since these graphs have concave Monge graphs, this can be done in n times polylog of sigma complexity. So for constant alphabet size, this is a good complexity, but we would really like to have a dependency on k rather than sigma. So what we do is we use the previous dynamic programming approach, and we want to improve it. And the first step to improvement is that we will reduce the possible candidates where we can split a prefix into its t-1 universal prefix and the one universal rest. So we will select a amount of possible splitting points, and these are exactly the last occurrences of each letter from the alphabet up to that point. Yeah, so for example, let's say we have an A here, then all of these positions where A is before that A are not really relevant to us, because in the one universal tail we only need one of these A's, and therefore the only thing where something interesting could happen is the last position of each letter before our current considered prefix. Okay, and if we reduce these candidates, then we only have sigma candidates left, and a direct implementation would yield a runtime of O of n times k times sigma. Now we introduce a technical data structure, and this data structure maintains a list of sigma elements, and it allows us to execute a sequence of operations, so sigma operations of this type down here. I will go to that soon, such that the amortized runtime of these operations is in O of sigma. Yeah, so the three operations that we execute in this order are that we can retrieve the minimum of this list and the index of this minimum. Then we can decrement some elements from an index onward to the end of the list by 1. And we can append a new element and increment the current size of the list by 1. And we will use that data structure to calculate chunks of our word. Yeah, so we will chunk our word into n divided by sigma chunks of size sigma, and for each of these chunks we will use the previous data structure to calculate all of its positions. So we initialize this, let's say this j sigma plus 1 position. We will initialize our data structure from the previous slide by using all of these last occurrences before this position. And we initialize this with these positions. And then we go step by step and go through this next sigma positions by always inserting it and retrieving the minimum, then inserting the next, retrieving the minimum, and so on. And since we have n divided by sigma chunks, and we can calculate for each chunk this sequence of these operations in the data structure in amortized O of sigma time, this whole method amortizes to O of n times k. Okay, so now let's move on to deletions. And for deletions, the main theorem states that if we want to lower our universality up to some k, or down to some k, then we can compute the number of deletions needed in order to do that in O of n times k time. Yeah, the idea here is also a dynamic programming approach, but we will use a completely different machinery, and the tools are different tools. And for example, here we will use range minimum GUIs. And then for substitutions, as you can remember, we need to distinguish here between increasing the universality with substitutions and decreasing the universality with substitutions. And for both, we can compute the number of substitutions needed in O of n times k time. And for decreasing the universality by substitutions, we will call a modified deletions version. So the deletions algorithm, we will call it, and instead of actually deleting positions, we will save the positions and substitute them by irrelevant letters. Yeah, so for example, for an arc that starts with a letter A, we can arbitrarily often insert this letter A such that it will never start a new arc. And therefore, instead of deleting, we will substitute these positions by that first letter of this arc. And that will yield us the same complexity and actually also the same distance in terms of added operations. On the other hand, we have the increasing of the universality by substitutions, and that approach looks really similar to the insertions approach, but we have more restrictions on this splitting position L prime. Namely, we need the prefix to be at least t minus 1 times sigma. Yeah, that is because we either use each letter as the letter itself, or we use it for substituting it by another letter. And the same is true for this tail that we want to make one universal. In order to make something one universal by substitutions, we either use each position as the letter that there is, or we need to use this letter as a resource to substitute it by a letter that we actually need. Okay, so we have these boundary restrictions here on the left and right hand side. Other than that, the approach is basically the same, but for increasing the universality with substitutions, it is important to say that they do not necessarily yield the same distance, because in this example, AABB, we would just need one insertion to make it 2 universal, but we would require 2 substitutions to make it 2 universal. Yeah, we could insert an A here, for example, but we cannot simply substitute one of them to make it 2 universal. Okay, so now let us go to the takeaways of our paper. So basically the main part of the paper is that you can calculate the distance of a word W to the k universality with respect to that word's alphabet in O of n times k and O of n space. Yeah, so for these dynamic programming approaches, you can calculate them row by row, and you don't need to store the whole matrix. And further, we can use k times sigma extra time to construct the actual word. And this can also be done in linear space using something called Hirschberg's trick. And finally, we would like to state some open problems. Namely, the first thing is that we would like some lower bounds to maybe show optimality of our approach. Then we would like to tackle the general word-word distance under Simon congruence, which seems to be quite hard, but that would be a nice goal. And for that, we can also first consider other word-language distances and consider these maybe interesting classes of languages that that we can check out. Okay, so this being said, thanks for your attention, and if you have any questions, please come to the Q&A session, and my colleagues and me, we will try to answer everything. Thanks.